Okay, hi everyone. Today we'll talk about diffusion models, their introduction, the model derivation, and the training scheme. So this will be first of the many lectures I'll be putting out to get a better understanding of our deep learning models and their mathematical foundations. Okay, so let's start with the introduction. So diffusion models are largely built on the framework of autoencoders or encoder-decoder models. So autoencoders are classical encoder-decoder models where, let's say, we have an input data sample X. Let's say the data sample is an image of a person, and this image is fed into the encoder, which is responsible for encoding X into a low-dimensional representation Z. So Z implicitly comes from a low-dimensional space of capital Z, which embeds the data samples into this project space. And when we have this latent small z, this is passed into the other module, other decoder, which is used to decode or generate the data sample X tilde. And so this framework of encoder-decoder architectures enables us to carry out inference over latent variables Z. And that is why these models are called latent variable models. And they are trained using variational inference. That is the ELBO objective, or evidence lower bound objective, which is a lower bound on the log likelihood of the data. So implicitly what these models are doing is likelihood maximization. So that's the VAE model, or the variational autoencoder, which is the bedrock of diffusion models. And diffusion models have this similar architecture of using an encoder and a decoder to compress or transform data and then generate samples from that transformed space. So in the case of diffusion models, the encoders and decoders can be considered as forward processes or backward or reverse processes. So the forward process is called the diffusion process. So during the forward process, what we do is we take the data sample, say we have X at time step 0, and we progressively add Gaussian noise to this data sample. So at time step 1 we get X1, and at time step 2 we get X2, which has more noise than X1. And so if we do this for enough number of steps, that is up till t steps, we get a completely noisy sample. That is, we have destroyed all structure in the data sample. And so this is the forward process. And if we carry this out for t steps, essentially what we achieve is a corrupted sample xt, which is sampled from a Gaussian distribution with zero mean and unit variance. That is the normal distribution. And the assumption here that we're making is that if we are able to destroy the structure of the data and we can generate samples from a noisy distribution, then we are solving a hard problem. So essentially the assumption is that generating data from noise is hard. And so this forward process that I described here, it implicitly forms a stochastic encoder, which is given by q of xt given xt minus 1. So given the previous sample xt minus 1, I sample a new data point xt, which is more noisier than the previous version. So that's the forward process. Now the reverse process is called the generation process. In this process, we try to reverse the diffusion process. That is, let's say we have a noisy data sample, completely noisy data sample coming from a normal distribution xt. That's the sample from the previous process. We progressively try to remove noise by iteratively generating samples which aim to retrieve the structure. And so if we do this, again, for up to t time steps, and able to reverse this all the way back to x0, the hope is that we should be able to retrieve the clean sample x0. And this assumes that we learn a parameterized decoder p theta xt minus 1 given xt. So given the next noisy sample xt, can I learn a neural network model that will that will give me the distribution over the next clean sample? And if I do this for many steps, up to t time steps, I should be able to end up with the cleanest sample, the data generated sample. That's x0. So that's kind of the high level overview of diffusion models. Now, what we'll be doing is we'll be studying a specific class of models, specific class of diffusion models called denoising diffusion probabilistic models, or short form is DDPMs. And as you can see from the name, DDPMs are diffusion models which generate data by denoising the noisy samples iteratively. So you can think of DDPMs as hierarchical VAEs, but having the same dimensions for all latent states. So in a hierarchical VAE, you have latent dimensions at different granularities, right? So say this is Z and you have the input X and rated sample X naught. So the latent here would have dimension, say, so the latent here would be Z1, here it would be Z2, and so on until I reach the actual latent Z, and then here it will be Z2 again and Z1. So each of these can have different dimensions. Say Z1 can be in the space, Z1 can be of dimensions, I don't know, 2048. Z2 can be of a smaller dimension, 1024, and Z can be of even smaller dimension, say 256. But in the case of diffusion models, if we compare this architecture with the forward and diffusion processes here, you will see that at each step we generate a latent or a sample X, which is of the same dimension as the input. So in the case of DDPMs, the latent will be X, and it will have the same dimension as the inputs. So that's a nice insight. We can draw some connections between BDEs and DDPMs and how they operate, and much of what we'll see is actually built on how BDEs operate. So the next thing I wanted to talk about was in general, when we train DDPMs, the encoder network denoted by Q is a simple linear Gaussian model. That is, we progressively aim to add Gaussian noise, but the decoder can be parameterized. It is parameterized because we want to learn to generate data. And so that's how we set up this problem, and we train this using maximum likelihood, which we'll see in the derivation part of this video. But you can think of, like, to get some more intuition, if let's say you want to run DDPMs on a 1D problem, then how will this look? So essentially, say you have an input data distribution, some pretty complex data, complicated highly multimodal data distribution, and at the next time step we add noise, which kind of destroys the multimodal structure of this data sample. So that's just one step of noise addition. And similarly, if we do it again, we get a much more simpler form of data. So that's Q of x2, and we can keep doing this again and again until we reach the uniform distribution, the noisy data distribution. So that's q of xt. So you can essentially link how the forward and backward processes run. So in the forward process, we go from data to noise, that is from left to right, and destroy structure. And in the reverse process, we go from noise to data, that is, we learn how to denoise the noisy distribution into clean samples. And here you can see that the final distribution that we have approached to u of xt is a normal distribution. So if you want to do generation, what we do is we sample from this normal distribution and we run this Markov chain backwards by sampling xt from p theta of xt plus 1. So that's what we do during the generation step. So essentially the entire process can be encoded as a Markov chain. Like in the first stage we run it forward, and then the second stage we run it backward. So just for illustration purposes, here is the Markov chain. So in the first stage we move forward by progressively adding noise until we reach xt, and here we do this using the distribution q of xt given xt minus 1, which is a simple linear Gaussian distribution. So this is Gaussian over xt given the perturbed previous sample 1 minus beta t xt minus 1 beta ti. So beta is a controllable noise schedule which typically is in 0 to 1 range, right? So I can easily see here that I am iteratively perturbing data by adding small amount of noise to the previous sample, controlled by the variance as well. So yeah, that's that. And we can compute the joint distribution over all these intermediate latent states that we come across by running this Markov chain forward. So this can be done, and this is written as x of 1 to t given the initial clean sample, and this is from 1 to t the product of individual distributions xt given xt minus 1. So that's the joint distribution, and this is a linear Gaussian Markov chain, right? Because everything here is Gaussian. Each like the individual distribution is Gaussian, and the product of these distributions will also be a Gaussian. So this is a linear Gaussian Markov chain. We can compute its marginal is also in closed form. So the marginal is written as q of xt given x naught Gaussian over xt root of alpha bar t x naught 1 minus alpha bar t of I, right, where alpha bar t is the product over individual alphas. And what is an alpha here? An alpha is nothing but, so I've just grouped everything into alpha, so each alpha is 1 minus beta of t. This is easy to see. If you just multiply all the chains, you will get this constant factor, and they can be clubbed as the product of individual factors. Okay, so that's the forward process, right? So this is the model. This is the joint, and this is the closed form marginal. Okay. The important thing to note here is the model itself. That's the most important aspect, because that's the distribution which perturbs the data and helps us run the chain forward. Okay, so this was the forward process. Now we'll talk about the reverse process, which will be in green. So the forward process is in blue, and the reverse process will be in green. So in the case of reverse process, we just need to we just need to go backward on the Markov chain, right? So say we have xt, we iteratively learn to remove noise from data using the parameterized decoder p theta, right? So for the forward model, we were using q. For the reverse model, we use p theta. And in this case, we know that the input x naught, we know the input is x naught, so we can derive the reverse process using one forward step. So let's say that we have xt minus 1 given xt and x naught. So the next clean sample given the current noisy sample and the initial data sample, this is written as a Gaussian over xt minus 1 given mu t of xt and x naught and beta tilde t of I. So the mean is the parameterized model, and beta is the variance schedule, or the noise schedule that we were using. So mu tilde t here is alpha bar t minus 1. Sorry about that. Alpha bar t minus 1 over root and beta divided by 1 minus alpha bar t. So this whole thing multiplied by x naught plus root over alpha t 1 minus alpha bar t minus 1 divided by minus alpha bar t times xt. So this might look a bit complicated at first, but essentially this is what this is saying analytically, is the mean is a noisy interpolation of the initial sample and the previous perturbed sample. And beta tilde here is the noisy schedule minus alpha bar t minus 1 minus alpha bar t times beta of t. Now this is a pretty complicated formulation, and also it makes a very strong assumption that when we are generating this data through one step of denoising, we already have access to x naught, which is unrealistic. Right, so in practice we won't have the data sample with us at inference time. We will have to generate data from a noisy distribution. We will have some conditional information, but we may not have the initial data distribution itself. So this is too big of an assumption to make, at least during the inference time. So in this case, we need to choose the generator in a different way. So the real way in which we choose the generator, or the practical way, is simply using the previous data sample. So the data sample decoded, that is xt minus 1, given the previous perturbed sample xt. This formulation is given by a Gaussian over xt minus 1, where the mean is parameterized over the previous sample xt and the time step t, and the variance is also parameterized over xt and time step t. So we can already see the connections with VAEs, where we use reparameterization during sampling and inference, and we only parameterize the distribution using its sufficient statistics, that is the mean and covariance. And we're doing the same here. We are parameterizing the diffusion model, or the generator, using its sufficient statistics, the mean and covariance. And this is very similar to VAEs in that we use the same form of parameterization, the same form of inference and sampling procedures to generate clean samples. So that's the actual decoder. And here one thing to note is that often at times this covariance parameterization sigma of theta, which is the covariance, is further written as sigma square t times the identity. So in this case, we don't necessarily need to learn a neural network with parameters theta. We can just use a schedule for sigma, or we can learn sigma for some amount of time steps. So that's the generative process. Here we have the model, which is the most important aspect in the DDPM formulation. Now, as we did for the forward process, we can write the joint distribution which is pretty straightforward because again we have a Markov chain. We just need to go backward and multiply the individual distributions to get the joint. So the joint distribution from x0 to t under this distribution p theta, this parameterization p theta is given as we start from the initial noisy distribution p of x of t. Then for t time steps we move backward in the chain from capital T to capital T minus 1 to capital T minus 2 and so on. And then we multiply the individual distributions to arrive at the final product. So let's look at it in the Markov chain. So here we have this distribution p of xt, which is the initial distribution, and the next step, like after one denoising step, we will arrive at xt minus 1 given xt, and so on and so forth. So in the case of x3, we will have x2 given x3. For x1 we will have x1 given x2, and for x0 we will have x0 given x1. Right, so nothing but the product of conditionals being multiplied in this linear chain, as we did for the forward process. It was x1 given x0, x2 given x1, x3 given x2, and so on and so forth until we reach xt given xt minus 1. And the starting distribution here was q of x0, which was the clean data sample. So yeah, that's the practical way of learning this, learning to generate data using DDPMs. The model is the most important aspect here, the parameterization of the Gaussian xt minus 1 given the mean mu theta and the variance sigma theta, which are learned to iteratively denoise given the previous noisy sample. So in the next part we'll look at the derivation of DDPMs and how they connect to the ELBO objective, that is VAEs. This section is going to be a bit long and it will have a lot of mathematical details. So before proceeding, it would be best if you can pause the video and revisit the ELBO derivation for the VAE. And now would be a good time to do that. Okay, if you have revisited the derivation for the VAE's ELBO objective, we can now proceed to derive the DDPM objective. So this is section 2 of this video, which is the derivation of diffusion models. Okay, so the derivation consists of 3 steps. So the first step is to expand the ELBO objective. The second step will be to simplify the ELBO objective. And the third and final step will be to eliminate the KL terms. Right, so let's start with the first objective, the first step, which is to expand the ELBO. So our objective is to maximize the evidence lower bound, and that will help us fit the model. So let's say that we have one data sample x naught. And so for this sample x naught, we can write the log likelihood as log p theta of x naught, which is equal to the log integral over all intermediate latents or samples multiplied by q of x1 to t given x naught times p theta x0 to t divided by q x1 to t given x naught. So what did we do in this step? We basically expanded the log probability of the sample x naught, that is over the entire chain. So let's draw the chain here. We have x naught, x1, x2, so on all the way till xt. Right, we expanded the log probability over the chain, and then we multiplied and divided by q of x1 to t given x naught. Right, so we just multiplied and divided by these terms. Okay, now we can see that this thing is upper bounded by the integral over d x1 to t q x1 to t given x naught times the log probability of xt product of t1 to t p theta xt minus 1 given xt divided by q of xt given xt minus 1. Okay, so what did we do? We did two things. First, we established a lower bound by moving the log inside the integral. Right, so we applied Jensen's inequality, and then we plugged in the joint distribution, the formulation of the joint distribution corresponding to p theta x 0 to t. Right, so this was Jensen's inequality. And this was the joint distribution that we derived in the previous section. So let me just write the joint distribution again. The joint distribution over p theta of x 0 to t was derived in the previous, or was obtained in the previous section using the Markov chain as p of xt, and the product of intermediate conditionals. So that's what we did, and we also expanded q of xt in the same way. So this term was also expanded in the same way as was the joint inside the product. Okay, so that was what we did. Now let's move on to the next step. Now what we can do is we can separate out the terms inside the log, and we can write the integral as an expectation over q. So let's do that. So we have an expectation over q, and then we can separate out the log terms by moving the log inside each of these and changing the product to the summation. So we obtain log p of xt, right? Very straightforward. Plus multiplication becomes a summation, and then we interchange the summations with the log, interchange the summation, and then we move the log further inside. So we get summation over t from 1 to t, and then we get log p theta of xt minus 1 given xt divided by q of xt given xt minus 1. So that is what we have now, and let's call this objective as L of x naught, right? So this is our simplified or expanded ELBO. This is the expanded ELBO, and we have given this name of L of x naught, and let's call this equation 1. Okay, so this was the first step of the derivation, where we expanded the ELBO and moved the log inside. And now we're going to proceed to the second step, which is to simplify this objective by simplifying the individual terms inside this ELBO. So the second one is simplify the ELBO. Okay, so one thing we can just write down before we proceed is the Markov property, which we will need. So if you look at this distribution q of xt given xt minus 1, we can write by using the Markov property that this is equivalent to q of xt given xt minus 1 and x naught, because the information about x naught is encoded in the previous time step of the Markov chain. And we can also further simplify this by using the Bayes rule. So the Bayes rule for 3 variables and this conditional can be written as q of xt minus 1 given xt and x naught times q of xt given x naught divided by q of xt minus 1 given x naught, right? So if we look at this again, what we have is that the conditional distribution, that is xt given xt minus 1 and x naught, is nothing but the product of the posterior xt minus 1 given xt and x naught times q of xt given x naught, that is the conditional over xt given x naught, divided by q of xt minus 1 given x naught. So this is something we will be using now. So we can simply plug this objective inside the first equation, that is L of x naught, our loss. So let's do that now. So plug in the above in equation 1, right, using these two facts simultaneously and putting them in equation 1. L of x naught as an expectation over q, and this q was from x1 to t given x naught, right, because this q was over all time steps for x, and let's start by plugging in and rewriting the terms. So the first term stays the same. We have log p of xt, doesn't change anything, plus now we're going to have to put in the term. So if we put in this whole thing, first we will write the log, and the numerator will not change. P of theta xt minus 1 given xt will remain the same. Now for the denominator, we will plug in this and we get q of xt minus 1 given xt and x naught times q of xt given x naught, and the denominator of that term will move into the numerator of this current term, which is q of xt minus 1 given x naught. Right, so pretty straightforward, nothing new. Now we're gonna have to break this term up into two separate summations to simplify. So this is an expectation over qx1 to t given x naught. We have the first term log p of xt, which is unchanged. Now we're going to break this from t equals to 2 to t time steps. So that's the important bit, that we're going to be starting from t equals to 2. And here we can see that the first term becomes log p of theta xt minus 1 given xt divided by q of xt minus 1 given xt and x naught. So that means taking these two terms together and grouping them in the log. Now we will group the remaining two terms again from t equals to 2 to t. We will group log of q of xt minus 1 given x naught divided by q of xt given x naught. So that is taking these two terms and grouping them together for time steps 2 to t. Now, but the job is not done, because if you look very carefully, the time steps in the previous equation start from t equals to 1. But here we have time steps from t equal to 2 in the second equation. So we need to account for the first time step. And this can be done. This is pretty straightforward, because if you look at it this way, this will come out to be log p of theta x naught given x1 divided by q of x1 given x naught. So why is this the case? Because if we look at this term, the very first term here, this holds for x naught given x1. So if we plug in t as 1 here, the first term, we will get p of theta of x naught given x1. So we know that this term is computable for t equals to 1. And the same goes for this term, right? Here if we plug in t equals to 1, we get q of x1 to x naught. So this term is again computable for t equals to 1. Now let's look at the other two terms. So if we look at this term and if we plug in t equals to 1, we get q of x naught given x naught, which doesn't mean anything because we can't predict the same input from the, we can't diffuse the input into the input itself. And similarly, if you look at this term, by plugging in t equals to 1, we get q of x naught given x1 and x naught, which again doesn't mean anything because we can't diffuse into the data term by having access to the data term and the noisier version of it. So these two terms are not tractable and not realizable. So we don't end up with these terms. We end up with the two terms that we have here: p theta of x naught given x1, q of x1 given x naught, and that completes this step. If you have any doubts on how we arrived here, it will be a good time to pause the video and revisit this step carefully. Okay, now that we have this objective simplified, we will individually simplify each of these terms to arrive at a much simpler objective. So one thing to note clearly is that this term can be simplified right off the bat. So let's call this term star. So if we expand star, we will see that it is a telescoping sum. That is, it is a sum which is iteratively cancelling out terms on its own. So let me just expand that and show it to you. The term star is a telescoping sum. How do we know that? Let's see. Star can be written, if we expand the term, star can be written as log q of xt minus 1 given x naught plus log q of xt minus 2 given x naught, and so on, plus log q of, and we plug in 2, we get x1 given x naught. So that is the numerator, that is the sum of the numerators that is expanded for this term. Now we'll do the same for the denominator. So for the denominator we have negative log q xt given x naught minus log q xt minus 1 given x naught minus log q xt minus 2 given x naught, and all the way to minus log q. If we plug in 2, we will get x2 given x naught. So you can already see that some of the terms are overlapping and cancelling each other out. So for example, we see here that log q of xt minus 1 given x naught is cancelled by negative log q xt given xt minus 1 given x naught. Similarly, log q of xt minus 2 given x naught is cancelled by negative log q of xt minus 2 given x naught, and so on and so forth. So if we iteratively expand this summation and we cancel out all the terms, at the end we will have only two terms left, and this star term will become log q of x1 given x naught minus log q of xt given x naught. So only this negative term and only this positive term will remain, and all other terms will cancel out. And so that's kind of nice because it simplifies a lot of the computation that we were going to do. And if we plug this star term back into our original equation, let's call this equation 2 because we simplified this from equation 1, so this is equation 2. And if we plug star back in equation 2, we get that L of x naught is equal to the expectation of q x1 to t given x naught log p of xt, just the first term which remains unchanged. The second term t equals 2 to t log p theta xt minus 1 given xt, and q xt minus 1 given xt and x0. That's again unchanged, and now we plug in star, which gives us log q x1 given x naught minus log q xt given x naught plus the final term, which is again unchanged, p of theta x naught given x1 q of x1 given x naught. So that's our new objective, and what we're going to do is we're going to write this as the negative ELBO now. So we'll just take out the negative sign and write it so that it's easy to understand from that perspective. So doing that, we get negative expectation q x1 to t given x naught is equal to the log p of xt given q of xt given x naught plus the summation from t equals to 2 log p theta of xt minus 1 given xt divided by q q of xt minus 1 given xt and x naught plus log p theta x naught given x1. Right, so what did we do here? Let's revisit carefully. If we look at the p of x naught term, it remains unchanged, and if you look at the q of xt given x naught term, this comes from this negation and it is put in the denominator of this logarithmic fraction, right? So we just combined this and this into one term. So let's call this term 1. Right, now what we did next was we kept this term unchanged. The second term is unchanged, and then what we did was we took the third term and we combined that into a single term because we cancelled out the log q of x1 given x naught with negative log q of x1 given x naught here, and we arrived at this this third term, which is log b of x naught given x1. So those are the three terms in our negative ELBO objective now that we can maximize or minimize depending on the loss function you want to use. But now we have reached a step where we can write all these terms as the KL divergence between different distributions. So to see this, let's move the expectation into each of these terms and write them separately. So this will give us the expectation over q x1 to t given x naught with the first term will give me the KL over q of xt given x naught with p of xt, right? So this is the first term as a KL divergence between the diffused sample with the distribution of diffuse sample given the original sample and the uniform or the normal distribution P of xt from which we start the denoising process. And we can do the same for the remaining terms. So for the second term from t equals to 2 to t, the expectation is kept over q of xt given x naught because the remaining expectations for q move inside to give rise to the KL, which is q of xt minus 1 given xt and x naught with p theta of xt minus 1 given xt. So that's the second KL term, and that's pretty straightforward to see. The expectation is remaining with q of xt given x naught, and the KL is over the diffusion process, that is the previous sample given the next sample and the denoised sample given the next noisy sample. So what this means is that we have a divergence between the original clean sample and the denoised sample, and we want to minimize that divergence. And then the third KL term is, this is actually not a KL term, it's just a simple log likelihood term, but the expectation remains over q of x1 given x naught, and here we see that we achieve nothing but log p beta of x naught given x1, and this is telling us to maximize or minimize the likelihood of the final diffused sample, denoised sample given the noisy sample x1. So each of these terms has their own interpretation. So the first term is telling us, let's assume that we are trying to minimize this objective. So the first term is telling us to keep the distribution of denoised samples close to the distribution of noisy samples given the the first term is telling us to keep the distribution, the initial distribution of the generation process p of theta of xt close to the noisy distribution q of xt given x naught. So this is saying to keep the initial distribution close to xt given x naught. So essentially this is imposing consistency, or you can say uniformity. In the initial distribution that will be used to, that we will be using to start our Markov chain from. And the second term is a summation of expected KLs. So it is saying that for each time step, right, for each time step, keep the distribution of denoised samples xt minus 1 given xt close to the distribution of originally clean data samples given the data x naught. Given x naught. And so this term is imposing, you could say, retrieval, or essentially this term is what is doing generation. So this is perhaps the most important term to maintain the structure of the data while also give us new samples. And the third term is, it's really nothing but a log probability over x naught given x1, that is to make sure that we adequately retrieve the final sample when we have denoised all samples up till x1 in the chain. So it's telling us to maximize this likelihood. So for the final sample, maximize its likelihood given previous sample in the chain. Yeah, so this is again something to do with consistency and uniformity, but it doesn't really do much with generation or diversity. Okay, so this completes step 2 of the derivation, and the third step that we will talk about now is the elimination or eliminating some of these KL terms to further simplify the objective and reach our final training objective. Okay, so one thing to note right off the bat is that each of these KL terms that we see here can be computed analytically, since all distributions are Gaussian. So if I focus on one specific term, that is, let's say, first let's write down that since we can compute these KL terms analytically, we focus on one specific term. Let's say we focus on the LT minus 1 term, that is the second to last term. So given that the data sample xt at time step t is, well, I can write it as alpha bar t of x naught plus root over 1 minus alpha bar t times epsilon. Right, it's just an interpolation between the original data sample, that is the clean sample x naught, and the noise epsilon t. So that gives me the perturbed or the noisy sample xt. I can write the mean as mu tilde t xt and x naught is 1 upon root over alpha t xt minus beta t root over 1 minus alpha bar t times epsilon. Okay, so what did we do here? Nothing much. We just write the mean of this of the tilted mean, the mu of this distribution using xt, that is our current sample, and the noise epsilon. And this is straightforward to achieve from our previous formulation of how we defined the mean in the previous section. So what this means is that instead of training the model to predict the mean of the denoised version, that is, instead of training the model to predict the sufficient statistics of xt minus 1 or xt minus 1 in itself, given the noisy input, x of t, we can train the model to predict the noise itself. We can train the model to predict noise. And from that we can compute the mean, because in this term there are only two terms which can be modeled, right? So it's xt and it's epsilon. Alpha and beta are constant schedules which can be either learned or hand engineered in the inference or generation process. But really we can model xt and or epsilon, but modeling xt is more difficult because data samples can be high dimensional and it can be a challenging problem to retrieve clean samples over t steps just by simply using the same latent dimension. Instead, we can base our modeling process over epsilon, which is the noise, and that may simplify some of the computational problems that may occur in practice. So using this intuition, we can compute the mean from the noise. So we can compute the mean from noise, and this can be done by defining mu of theta xt given the time step t 1 upon root over alpha t times xt minus beta t root over 1 minus alpha bar t epsilon theta xt and t. So this is pretty much the same formulation, except that we have parameterized the noise instead of the data sample xt. So we will model the noise using parameters theta and with this parameterization we can go back to our initial loss that we had defined here in these KL terms for one term LT minus 1 here, and that can give us the final loss over the terms. So the loss averaged over the entire data set will become LT minus 1, right? So just for one time step LT minus 1. If we compute that, we get this mean plugged into the LT minus 1th term for the KL. So that will give us expectation over x0 sampled from the initial distribution x0, the true noise sampled from a unit normal distribution, and the schedules come first. So beta t square times 2 sigma t square alpha t 1 minus alpha bar of t multiplied by the actual L2 loss on the noise. So the epsilon is the true noise minus epsilon theta is the noise that we predict or model using our noisy network or neural network. So this gives us alpha bar t x0 plus root over 1 minus alpha bar t epsilon with t, right? And that is the loss term. So in this noise modeling framework, if you look very carefully, we will see that root over alpha t bar times x0 plus 1 minus alpha t bar times epsilon t, this is the sample at time step t. So we try to predict the noise inside the sample at time step t, where we target is the true noise epsilon, which is sampled from a normal distribution. And another thing about this loss is that this objective, although it does correspond to maximum likelihood, empirically it is seen that the loss works best and the model provides better looking samples when this entire thing, this noise schedule and all these constants are clubbed into a single term, let's say lambda t, and they're set to 1. So really this entire term can be simplified into a loss, let's say L simple, which is the expectation over x0 sampled from q0 x0 epsilon sampled from uniform, and epsilon sampled from a normal distribution, and the time step can be sampled from a uniform distribution, and then we just model the noise in our current sample x of t. So this is the final objective for training DDPM diffusion models that is used in practice. we went through a lot of steps and the math became a bit complicated. So it is highly encouraged that you review the steps and the individual components of each of these steps which lead to this final objective, and also the assumptions that we make along the way. So if you want to do it, now would be a good time. And if you have reviewed these steps and the entire derivation is clear to you, then what we're going to do is we're going to set up the training scheme for DDPM like models, and we'll also discuss how we can do sampling and inference in diffusion models. Okay, so this is the final section of this video, and it won't be too long. So let's talk about training and inference. We start by looking at the training of the DDPM model using this L simple loss. So for training, we will need each of these three things that I've highlighted: the data sample x0 from the initial distribution. So x0 is sample from q0 of x0. We will then need the time step, which we sample from a uniform distribution. And then we will need the noise epsilon, which we sample from a normal distribution. So these are each of these three things that we need: x0, the data sample, t, the time step, epsilon, the noise. Now that we have this, we can train the model by taking a gradient step on the L simple loss. More formally, we compute the gradient with respect to theta of the terms which are inside this expectation. So that's the training step. So this is one step of training, and we can do this iteratively until convergence or some criteria is satisfied, let's say reaching a fixed number of epochs. And that's the training algorithm. So let's put that in a box. So that's how we train the DDPM model. Now let's look at the sampling, which will require us to run the Markov chain backward. So for sampling, we first need the corrupted data point, that is the noisy sample. So let's say we get that at time step capital T, which is the terminal step from a normal distribution. Now we will run a Markov chain backward. That is, we will iteratively refine the sample by passing it through our model, that is running model evaluations to arrive at the final denoised sample. So for each small t step, that So for each step, we will move backward from capital T to 1, and we will do two things. First, we will sample Gaussian noise, which is a reparameterization of the previous sample, and then we will compute the previous sample by denoising it from the current sample x of t. So this is nothing but the previous terms that we discussed in the first section, but we will plug in our approximation of the noise using the diffusion model, the denoising network x of t, and then we add the reparameterization, that is the noise. So let's take a look at what this second step is doing. The first term is just a scaling factor. The second term is xt, which is our noisy sample at time step t. And the third term is removing noise from this noisy sample iteratively using our approximation epsilon. And this last term is nothing but Gaussian noise. It's a reparameterization so that we have tractable approximations. And we can do this for t steps as we do in this loop. And once this loop exits, we will return the final sample, that is x0, which should be the clean sample. So yeah, that is the sampling and inference procedure. Let's put it in a box, finalize this. Okay, so that was training and sampling using the DDBM framework. Now let's talk about some practical tips and tricks that are used to train DDBM models. So one thing to note is that traditional models of vision, that is, that use high dimensional inputs, use sophisticated architectures like convolutional models, CNNs, and of lately transformers. So pixel inputs or images are fed to CNNs or transformers or a mix of these models, and diffusion models are also in this category, that since they operate on high dimensional inputs, they use similar architectures. But one thing to note is that diffusion models use a very specific kind of architecture for stability purposes, and this architecture is called the U-Net architecture. So the U-Net architecture is just another convolutional transformer model, but it consists of intermediate skip connections between layers. So it has intermediate skip connections which run from earlier layers to later layers. And there are two reasons why the U-Net architecture is being employed. The first one is for stability purposes and to get the learning to improve, that is, to have a stable gradient signal, especially when we're dealing with large data sets. And the second one is for sample quality. It is empirically known that U-Net architecture provides the best sample quality when training diffusion models. So the traditional training pipeline looks something like this, where we have, let's say, a data point, an image which is like, let's say it's an image of a person. This is the data at xt, at time step t, and it is passed through these hidden layers. And the output is the predicted noise parameterized by theta. It's epsilon xt times step t. And we also have the time step, which is fed as input to the model. So the time step is nothing but a vector encoded representation of the time, which is first passed through a few fully connected layers, and then it is concatenated to every single layer in the network. You can choose to not concatenate it as well, but it is found to be beneficial to concatenate it in the intermediate representations. And as I mentioned, this is a unit architecture, so there are skip connections from later layers to from earlier layers to later layers. So there will be skip connections from this layer to this layer, this layer to this layer, this layer to this layer, and so on. And this provides stability to the model. Now, that was the explanation for how DDPMs work, their background and their details. If you're interested in more diffusion models, there are additional resources you can check out. So the first thing to look at would be the DDPM paper, and it provides a lot of information on the choice of parameterization and the results that DDPM achieve. Then there is DDIM, which introduces implicit models, also simplified DDPMs. And if you want to dig deeper into the training scheme and how these models are trained or accelerated, then there is chapter 25 of this book called Probabilistic Machine Learning, Advanced Topics. So these additional resources will give you a much better and deeper understanding of diffusion models. So that's it for this video. If you have any questions or concerns, feel free to drop them in the comments, and I'll try my best to answer them as time permits.